Well, so what are we here for? We're here because we have a quiz next Thursday. I'm trying to adjust this folder. Okay. Okay, so we have a quiz this Thursday, and guess what? This is the last class meeting. What can we say? Last class meeting of a lecture. Next class meeting, you come to class and I'll have sent you the test copy. And there's no lecture. When you finish it, you can just go on to other things. What else? We're going to review for that test now. There's 12 questions. I think it's pretty short, but some of the questions are technically detailed. So we're going to go over that right now. And all the questions of history and Ada and Babbage and who started what, there's none of those. We're just going to do straight modern computer science. All right, so let me start our little review. And then that will be the end of assembly for spring 2022. Okay, so I'm going to switch the camera back to the desktop. Okay, so let's 2 days from today, Thursday, is concepts at class time, 2 p.m. And it's 12 questions. And I can't cover everything done this semester, but these are going to be 12 randomized questions from the whole semester. I think 3 of them are GDB, by the way. GDB. Okay, so let's go over some areas that you should brush up on. Okay, I have a list that I made earlier today in handwriting. One thing is to know about the problem of adding a large and a small number together. Issues of arithmetic on large and small numbers. Okay, that was discussed one class meeting not too long ago. So what if you, I'll go on and maybe we'll come back and solve a problem. What would you do if you were faced with 10111101 times 2 to the 11 plus 1011101111 times 2 to the minus no, that's too much, 16. See, one number is big and one number is small. How do we handle that? And the question is, how much data gets lost in simply adding 2 numbers? Okay, we can solve that, but let's go on and finish the whole list. Okay. No, here's getting the details. Memory management MANAGE, management, including memory dump. That's part of it. Dump. A memory dump is just a raw display of what's in memory without any special effects. No, nothing, no arithmetic has been applied. You just dump out all the memory. And within memory, can you find the current activation record? And the second part of that question is, can you find the dormant activation records? ACT records. Okay, there's a question coming, and some suggestion. How do you study for that? Well, you need a memory dump. See, in order to practice doing this. So get a copy of the program called Stack Frame. And run it. And at the end, it will create a memory dump, which you can experiment with. It'll be very similar to the one that comes in your test. I should, in the function, here's what it looks like. You need to know. See, that it's a program, but main calls SF1, calls SF2, and I think that then calls make stack dump. Okay, this is C++. Inside there's a call to it that looks something like I can't remember exactly. K equals stack. I think it says stack frame. And there's 3 numbers: first, second, and third. Okay. The first one is any integer, 277. That's just an identifying number. It has nothing to do with anything. The next number is like how many quad words do you want to see at addresses lower than the top of stack? So these are quad words outside the stack itself. Mostly those aren't interesting, and you could even put a 0 there and say, I don't want to see any of them. But the third one really counts. That's how many quad words you want to see in your memory dump. Number of quad words, like 80. Okay. That'll give you a nice size dump out of your whole stack. Okay. All right, that's for practice exercises during the next 48 hours. Let's see, let's go on. Well, and while you're doing this is to practice the linked list issue in memory. Linked list. You need something to practice with in order to understand that. Let's see, I have other notes here. You should know about, let's see, know is the wrong word. It should be replaced with be able to find. Okay, in an open note test, open the internet, open computer, open everything. It's not that you have to memorize all the facts. What's important is you'll be able to go to the answers easily. Okay, so know about inline programming. Know where to find it in inline programming. Inline programming. Okay, and remember the lecture that day. This is for those people or those companies that do not have an assembler installed. They don't have anything like NASM installed on all their employees' desktop computers, none of it. So those employees who are programmers use inline programming to get around that issue. So you should know about it. If there's a question on the concept test, you'll know directly where to go find the answer. Okay. Let me see, what else do we need? My list here. Somewhere I wrote down students should know the geometric summation formula. Geosum formula. And you can find it in any calculus book. It looks like this. It has to stop someplace. And there's a real number here with an exponent. So it looks like real number to the 0 plus real number to the first plus real number to the second plus dot 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 real number to the n. Okay, and where we use that is if a mantissa starts repeating itself. You might, it's kind of hard to evaluate what is the value in. I mean, you could use your calculator really hard in it for 20 minutes, you can do it. But what if your mantissa looks like 1.100, 100, 100, 100, 100, and so on. This definitely stops out here someplace. Okay, you can evaluate that exactly if you apply this formula up above, and it'll save you a lot of calculator work, hand calculator work along the way. So let's finish the list, and at the end, if anybody's interested, I'll actually do one of these, and you'll see how it works out. Okay, that's when you have to translate. Let's put it down. You're converting between IEEE 754, either one, 64 bits or 32 to decimal. Can't write it in there. Okay, so some of these numbers, IEEE 754s, are nice, nice expressions, but some of them are not so nice. So, for instance, well, 0x4048, and everything else is 0. You don't need a hand calculator for this. Okay, but some are not so nice. What if it's a repeating one that I'm talking about? 0x409. Let's see. What is the 3? I probably can't remember it. 3, 6, 3, 6, 3, 6, 3, 6, 3, 6, 3, 6, 3. There's for it. And so that's a repeating bunch of bits. That's not so nice compared to the one above it. So, okay, so be able to, it's a short test in number of questions. So it won't cover everything, but be prepared to convert between our two kinds of floats. IEEE 754 in 64 bits. Generally, when you write this word, Plies hex. They don't write IEEE's and anything else. Back and forth between decimal. And also the 32-bit kind. E 754 32s. And back again. Okay. Let me see. And then look at the next page. I'm missing something. Listen here. Oh, did I write it down yet? We did inline programming, and then don't know it. You don't have to know it, but you have to be able to find it. Program of pure assembly. Pure assembly. Okay, so one way, I don't think pure is a standardized word. Where would you see? Okay, so I know at the class website, I know there's 2 such programs. I'm trying to remember if the ebook has one. I kind of think that a lot, the answer is yes. The ebook by Jorgensen, but I don't think he calls them pure. I think he just calls them, these are assembly programs, as assembly with no library functions. No library function. And of course, that means no driver. And the word main doesn't exist there. So there has to be a substitute word for main. Main, M-A-I-N. What is main's replacement called? And there's some people in the world and some companies who program that way. They don't have C or C++ available. A lot of these people are programming for device drivers. A driver is a little program that allows you to connect one piece of hardware with another, like plugging in a USB stick. Once it gets plugged in, a device driver takes over and enables your program to save files on the USB drive. So that's an industry all of its own. It's creating drivers for products, and I'd say, I don't know, 98% of that is written in assembly. The vast majority of drivers are. Okay, I'm still looking for my list. What happened to my list? Okay, I can't see. I'm missing something, class. Did I do, no, it's fine. Well, where's my, upwards, no. Did I talk about the memory dumping? Yeah, that was the suggestion of, you get a program that I had posted. Okay, so I may have to open up the machine here and look for it. Be aware of integer operands with mul and div, or for that matter, imul and idiv. Okay, these are two cases. I don't think this applies to add and subtract, but it applies to multiplication division, that if you multiply two numbers, multiply will result in an overflow of two integer registers leads to two registers, RDX, RAX. They take the huge overflow number that's overflowed the size of one register, and they split it between two of them. Okay. And idiv requires the reverse of that. To do a correct division, it's not enough to put your numerator in RAX, like such. Move RAX 3,847 and move the divisor any place, RCX 321, and then do an idiv, RCX. That's incorrect, because idiv assumes that you put this number, the divisor number, in, no, I said that wrong. It assumes you put the numerator in two registers. This one here, even though it fits in one, this division is going to use two registers, and there's that pair again. It's going to use RDX, most significant bytes, RAX. It's always those two as the least significant bytes, and idiv assumes that you've set this up correctly. Okay. This is called a concept test, but I think 3 questions have it where you have to write a block of assembly statements. So there is some programming in the concept test, but it's not programming. We don't run it exactly. I'll just grade it by looking at it. 3 questions have GDB involved out of the 12. And GDB has two components that we could view. One is where you look at things, call it viewing data. And the other component, I had plans to get to it, but the time didn't allow it, was to change data. Okay, this second part's not on the test. Not. But this part is somewhat like our midterm. This is on the test. Is. Okay, so I'm going to ask you questions that come from the area of show the value in a C++ variable. Show the address of a C++ variable. Show the address where an array is stored. Where it's stored, show the address of last element in the array. Show the contents of a string variable. All those that I just named are stored in C++. So showing C++ data. And that includes pointer data, including strings. This kind of string, S, and this kind of string. So the show data commands you should focus on are the whole gamut about showing different kinds of outputs. Output may not be the right word, showing the contents of all kinds of data. And that includes GPRs, and it includes their group name is called SSE. But we refer to them as the XMM registers. Okay, know how to show values in any of those. And part of showing is how you break it up. What could I give that as example? See, XMM registers have, we normally think of them as two registers under the same name, each are 64 bits. But you don't have to think of them that way. I'll try and, instead of saving this to the very end, let me just see if we can do one right now. Okay. If I want to show the value in XMM3, the low end, it's, do we have to use, I don't think, okay. Here it would look like, X, there's an X, I can't write very well. 4.v2 dash double 0. Okay. What, but that's assumption you're looking at it in terms of splitting the whole thing in halves. Some people look at it as splitting it in force. And that would be P/X and register name V4 underscore. Is that double means 64 bits, so this has to be 32 bits. That would be float. And then you can name any one of 4 from 0, 1, 2, or 3, like such. I'm a little bit worried about the X. Does anybody remember if X is the right thing? I'll have to run a program quickly. It might be F for float. In fact, the more I think about it, I think it requires a PF. Okay. I'll tell you why in just 30 seconds. So there's examples of breaking up the 128 bits, this in halves and this in fourths. You know, showing something in hex, this is strange, but it's true. It falls in the territory of integer data, even though it's a float number. When the machine starts to treat those bits, it's looking at it as if they were just the bits of an integer. And so if you want to see one of those numbers in hex, you make it think that this is an integer request. Here's why I caught that mistake earlier. P/X $$ XMM12 V2 underscore INT 64 brackets 1. Okay. See, and then it will give you the bits stored in here in raw form without managing them into or converting them into decimal float. That's what this is doing up here. Okay. So that's how you get the hex, the IEEE expression for what's stored there. How did I get on that tangent? Oh, the GDB is all about viewing things, not modifying data. And that includes the SSE registers and the GPR registers. We never did this part, so there won't be any question about that. If you were to change, if you had a variable in C++ declared, set equal to 3.75, semicolon, and then you run GDB, you can change its value right in place, and it would look like the set command, set cost equal 5.05. There's no punctuation on the end of it. It just looks like that. We're not doing that. It's something for another day. Okay. Class, let me take, I want to check my, it says looking at my handwritten notes, I have some more on, I got to plug a flash drive in and check and see. Let me see if I'm not missing anything. Okay. The thing's booting here. Let's find out. Okay. And where is it? It's looking. Still looking for it. I think I found it here. We'll have it in a minute. It's coming. Okay, that's I had part of my list in electronic form. Okay, it says, I think I mentioned it, the problem of large numbers and small numbers. You know, we talked about that. And inline assembly. We talked about that, inline assembly. Next one. There's if I ask you to write a block, in fact, there is a question, we have to write a block that performs arithmetic on XMMs. I think this is really standard stuff. Block of instructions on XMMs. And that, well, that's not a deep one, but let's see. And oh yeah, did I mention? I mentioned pure assembly, I hope. I hope I did. Well, I can't see it. Let's put it on the list, everybody. There's a question about pure assembly. Now, where to find examples? Pure assembly has no driver. I think I mentioned that. It has a funny main. It doesn't call itself main. It calls itself start. You should look how they the starting assembly function starts up. So you need access to an example. And I think you can answer the rest of the questions on that subject. And standard conversions from before the midterm, you should know that we are going to go from IEE 64 bits to decimal, and also the new guy on the block, IEE 32. We're going to translate into here and back. So there's 4 directions. Any one of those is a possible candidate on your test. And yeah, we got those. See if I have covered all. And we're getting close to the end of my list. Activation records. Know how to find the linked list. How to find the list of ARs in memory. And well, I'm almost done with this list. One more thing that occurs to me is know what happens, or how to look it up in your notes. Know what happens when C++ calls another function. This is pre-midterm material. Another function. Okay. You need to be able to explain that in terms that an assembly programmer can make sense out of. What gets pushed onto the activation record, what starts the new activation record, how the back pointer moves forward. That's what this question is after. And the reverse of that is know what happens when our return is executed. In C++ and C, we have these statements. Is executed. Now, it's not good enough to say, well, execution goes back to the caller and continues. That doesn't tell the assembly programmer anything. That might be good for a freshman in the first class of C++ programming. So we want an assembly type answer here that tells us what registers change and how they're changed. Okay, since we don't come together for discussions anymore this semester, let's, I should say some things about the programming test. So next week, not this week, there's a program to create. And I want to make it clear that you got to send me your best before the time's out. If it, we'll look up their time later. Now this is not for most of you, but for a few, you can't send me a replacement program 6 hours after the test ends or the next day. You get the 3 hours. When the 3 hours is getting close to the end, you got to send me a good program. It's here's a, I mean, it's kind of sad, but people have done exactly what I'm going to explain here. Here's a bash file. People working on the bash file and they got good executing statements in here, and that's fine. Here's a program over here. This is the driver. And it seems to be all working. And this person or persons ready to submit this. And they say, oh yeah, he wants my name and email address on every file. So you copy the over here. It's all written nicely. Name, email address, section number, you're enrolled. Copy this, paste it over here, submit it to the teacher. What's wrong with all that? You know what? Bash file doesn't run. It just crashes immediately because over here, the comment lines start with double slashes. The number of students copied this comment and pasted it over here. It doesn't start with double slashes here. The person never tested their own bash file before sending it to me. If you had tested it, you would have known, he or she would have known there's got a problem I got to fix. So please, I can't fix errors, big or small. You got to do one more test after just 30 seconds before you send me the email. Test it one last time. Test your run one last time. Then email it to me. It'd be a shame to lose points just because the bash file is misconfigured. Maybe just by accident it got that way. Oh, okay. What else do I have to say about that is it's okay to, and I've said it many times, I'll say it again because it keeps happening. It's okay to do half the specification or a third of the specification. If you're running out of time, I recommend when you first see the description of the program, take the smallest piece that you can imagine that will run by itself and just implement that. And if there's time left, you can work on more pieces. So I give you a big problem description, and 90% of the time I even give you a suggested calling diagram. I usually start off like this. Do this, input data into an array here, call on is float here. And there's other stuff that's going to happen. We're going to sort the array. We're going to display the array. We're going to find the grand average of everybody in the array. But I'm all against, and I apply it to myself. I'm against doing it all at once. If I'm approaching this, I will build a part of this enough to make this call, and enough of this to make this call. And this one, I'd probably try to complete it. And so I'd end up building just this much. And I want to see it run without errors and successfully complete itself. Then, and that's, I don't know what that's worth. It's a blank program is worth 20. That's probably worth 35. And if you can add one more to it, you still have time, then add this one to it. And draw your circle around this much of it. If time elapses and, when you do one part, you can send it to me that much. And if you are able to add another component to it, then send me the upgraded model and I'll upgrade only the newer one. Maybe you can work your way across the whole lower level of functions one by one. But it's an individual decision how to attack it. I think what I'm proposing here will yield the most partial credit points of any. That's why I'm advocating it. Okay. What else? What else? I never asked where you build your programs. Any computer is okay with me. I was going to teach computing in the cloud at CSUF has a cloud computer. How you can run assembly and C++ in our own cloud called Titan V actually. But we ran out of time. So you can build on any computer you like. And you don't have to tell me. But you need to be able to test your bash file at least the moments before you do send it off to me. I remember students who run on a Mac just natively, no extra. You have to, I don't have the Mac, but students who did that in the past, they do some kind of setup like the way you activate WSL, but Mac users activate something else. And they're able to use a terminal window and what do they, I don't know if they assemble with NASM or it's a built-in assembler. But I'm just saying that it can come from another platform, and I'm okay with that. But you have to get the line endings changed, and it has to run on my computer because I can't maintain all those others as test cases for things submitted to me. I like all you students, but it doesn't do any good to say, but it runs on my computer. I don't know what specialization you have. I have a very generic, plain vanilla Linux-based box that runs most everything in this classroom. Okay, are we about done? Last look at notes. I think so. Okay. Looking one more time. I think this is okay. Okay. I think we're good. Any questions, anybody? Okay, if some special news happens, I'll send you a broadcast email between now and next week. I don't expect anything to happen between now and concept test in 2 days. 48 hours from now, we'll all be done with that. That should be pretty normal stuff. 12 questions. And I don't think 2 hours should be way enough. Half of you will finish in 1 hour, I think. Okay. What else I think we're done. Okay. Okay. Let me look at the questions here. Yes, I see something here. How much time do we have for the con? That's easy. It's the full 2 hours that would normally be class time. But think of it, 12 questions is a lot better than the 28 you had on the midterm. Show how to use the geometric sum. Sure, I can show you that. Let's do, can I write on the back side of this? Maybe. Let's do that. Okay, so We need a geometric, we need a repeating mantissa. Let me try to make up one. In 64 bits, let me put this wire here. Let's pick a nice number that's not too complex. 0x404. And then, trying to think of one here. What I'm trying to think of is, let's make this the mantissa. 0, 0, 1, 0, 0, 1, 0, 0, 1. And this just goes on forever. Okay. And there's probably a 1 here times 2 to something. Okay. Now, sometimes you can't see the up here, the repeating part. So if I block that off in 4s, uh, 0, 1, 1, 0, 0, 1, 0, 0, 1. Okay, so there is a pattern here. You know, here's a 2, here's a 4. It comes by 2, 2, 4, 8, but here it is 2, and this will be a 4, and this will be an 8. Okay, so suppose our starting number was 404 for exponent, then 2, 4, 8, 2, 4, 8, 2, 4, 8, 2, 4, 8, 2. See that mess? That's a real ugly mess. But in bits, it's not too bad. It's 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1. So the question is, how do we solve that? And how does that formula help? I'll show you. Okay. I need more paper. Okay. So let me, you know how to deal with the exponent. I want to deal with mantissa stuff. So what that expression means is we have a 1, that's the hidden bit here, and then it is plus, this will look tedious. The first one is 1/2 to the first, plus 0, 1/2 to the second, plus, now we hit the 1, 1/2 to the 3, plus 0, 1/2 to the 4, plus 0, 1/2 to the 5, plus 1, 1/2 to the 6. The 6 is here, the 1/2 is here. Okay, you see, by counting by 3s, 3, 6, 9, 12, those are the ones that count. The others have zeros on them. Okay. So the ending one, so it's multiples of 3. In this example, it's multiples of 3. I'm going to skip over those. And it'll be 1/2 to the 12 to the 9, dot dot dot, plus 1/2 to the 12, plus dot dot dot, 1/2 to the 15, and there's 52 terms. Let's see. 52 is divisible by 3 exactly. 17 times. No, that's not quite right. 17, 51. And 1 left over. Okay, we're going to have 17 terms, and then there'll be a +0 term, which we throw away. So it keeps on going, and it will be a 6. Let me get it right. 60. There'll be 1/2 to the 48 plus 1/2 to the 51. There's one out here, but it's a 0. 1/2 to the 52. Okay, so what I have is a whole collection of multiples of 3. Here's our mantissa being evaluated. The 1 is 1/2 to the 0. Everyone agree? Anything raised to the 0 is a 1. The next term is 1/2 to the 3. The next term is 1/2 to the 6. And the last term is 1/2 to the 51. Okay. If you watch, we're getting closer to that magic formula. Now, the formula doesn't let you jump by 3s. It says you must jump by 1s. So we can fix that. That's 1/2 to the 0. Now, inside, what I'm going to do is, see, okay, I want to make it 1/8. How can I show you? This is 1/2 to the 3 raised to 1. And this is 1/2 to the 3 raised to 2. Dot, 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 plus 1/2 to the 3 raised to 17. And there it ends. Now I'm not skipping. My exponents go 0, 1, 2, 3, 4, up to 17. And I can clean up the writings, make it look a little nicer by doing this. 1/2 to the 0 plus 1/8 to the first plus 1/8 squared plus 1/8 cubed plus dot, 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 1/8 to 17. Actually, I want to make that an 8. That's it. That's that geometric formula. If you like calculus, they would over there write it like this. K equals 0 to 17 of 1/8 to the K. That's our formula. The formula says that number, now this isn't even round off, this is actual pure 100% accuracy. The formula says you make a fraction on the denominator, you use 1 minus an 8th. In the numerator, you use 1 minus an 8th. The whole thing raised to 1 digit higher than this 17. So that would be raised to the 18. Now, I'll clean that up a little bit. That fraction on the numerator is 1 minus 1/8 to the 18. And the denominator is 7/8, which becomes 8/7. 1 minus an 8 to the 18. Okay, that's the mantissa. Okay, but the original problem had an exponent. Did it have an exponent? Yeah, here's the true exponent. Here's the stored exponent. Now, stored exponent 404. And in 64 bits, we subtract the bias number 3FF. Did I get that right? I think the stored exponent is a 5. But okay, when you subtract here, oh, I see. You have to borrow from here, so you take this, and this becomes a 10. Take one away, and it becomes an F. This becomes a 14. F from 14. 14 is really 20, and F is a 15. The answer is actually 5, 0, 0. Okay, well, that true exponent happens to be 2 to the 5. So what I calculated here on this page here was the mantissa part, all of this. So now I have to take that answer and multiply by 2 to the 5. And we'll call it final answer. Equals 8/7. 1 minus 1/8 to the 18 times 2 to the 5 is 32, or 2 to the 5. Okay, we can't go any further now without a calculator. This part in the middle is not good for humans. This is good for a hand calculator right there. So, but up to that point, it's 100% accurate. That's really what the computer is holding in that original number that repeats back here. Okay, if it doesn't repeat, it's like pi, you're screwed. You can't do anything mathematically. If it ends in all zeros, you can do that one. That's not that bad. And if it ends in a repeating one, you can still get an answer, but it takes extra work. You saw I had to go through all these steps to manage all those terms to get them just right. Otherwise, what would my choice be? I'd have to use a hand calculator and add this 1 as a starting place. Start with here. And then I have to calculate this in and add it in. And then I have to calculate this one and add it in. And then this one and add it in. And I have to do that 17 times. You'll still get a number that's the same, but it's the number you'll get is this one. Okay. Okay, can we show how we would use, I got that. No, we got it. This is it. You wanted to know. That's how you should handle a repeating mantissa. I'm not saying they're easy. I'm just saying you can do it. You can do it, no matter what's repeating. What's something like 407. Well, you will practice this one. 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, 8. Okay. There's a repeating one. It's a 1 and 3 zeros. 1 0 0 0 1 0 0 0 1 0 0 0. It has a nice answer, but it's. I'm not saying it's a clean path. It's a kind of a messy path to get there, but you can do it. You can try 402 FFF. How's that one? That's a mantissa that's all ones. That's not bad. How about a 400? What is it? We could do 400 111. There was something else I was thinking of. One. I can't remember it now. A. A is 1010. See, so it forms a pattern 10101010. Same technique. Yeah, that's not hard. It's a little more harder when the pattern spreads over 3 digits. This pattern was 248, 248, 248. But it's not impossible. It's just more tedious work. Any other questions, anybody? He says it makes sense. All right, you got it. You see this is geometric sum is not really calculus, but that's where you usually find it described. Somewhere in a certain chapter on Maclaurin series, you'll discover they have this formula. So that's where I borrowed it from. See, there is something worthwhile out of Math 150A, or most of it's not useful, but little things are useful. Okay, anybody have a question for me? Okay, the student who told me he takes this class while driving in a car, man, you got to park it and write your test answers. You can't keep driving. This one time at least. The rest of you, I hope you're sitting at nice tables where you can have easy access to your material and look up good answers. Okay. I'm all done. I'll be here until 4 o'clock. Anybody want to hang out and ask questions? That's fine. If you have things to do, that's fine. I hope you have a great summer. I won't be talking much the next 2 times we're together, but hope you have a great summer and come back and learn other parts of computer science next fall. Have a nice afternoon, everyone. The sun is shining.
Oh, wait, Professor, I have a question.
Sure.
So just like the previous exam, if we manage to get the code portion to work on our end, but it doesn't work for you, should we just write like just like a precaution? Should we write like, oh, we use this, we use like Tuffix, or we use this part to run it? So that way you know.
You should tell me that. Here's the track record. Everything that no one has ever sent me something they said was made in WSL that didn't also run for me. There have been a few, but they're rare, a few rare cases of a Tuffix. It comes to me and it doesn't run. I still like Tuffix. It's a good place to learn, but there have been a rare cases where the Tuffix program didn't run for me. So I invite you to tell me about your platform, and I'd be totally shocked dead if a WSL didn't run also on my computer. But Tuffixes on rare occasions have had issues. And if you tell me about it, I'll run it on a second computer just to make sure it isn't my computer that's causing the problem. Is that okay?
Yeah, so make sure, just basically just maybe get the caution.
Yeah.
Yeah, I would say so. Okay.
Yeah, I'll take the precaution. I recommend you say so.
All right. Thank you, Professor.
Sure, you're welcome.